Superconductors at room temperature, which are substances that conduct electricity without resistance and don't require special cooling, are the kind of technical marvel that would completely alter daily life. Numerous other potential uses include the ability to create levitating trains, quantum computers, and revamp the electrical infrastructure. But up until now, superconductors could only be used in a narrow range of technologies because they needed to be cooled to very low temperatures. Kamerlingh Onnes made the discovery of superconductivity in 1911 while researching the resistance of solid mercury at cryogenic temperatures, utilizing freshly created liquid helium as a coolant. He noticed that the resistance immediately vanished when the temperature reached 4.2 K. Only after Onnes' notebook was discovered a century later could the specific date and circumstances of the finding be determined. Many superconducting materials have been found since mercury's superconductivity was discovered. Superconducting materials can be categorized into a number of groups depending on their components and structural characteristics. Metallic materials, such as intermetallic compounds niobium stanides and aluminates, and magnesium diboride. Alloys such as niobium, titanium, and germanium, and pure metals, such as mercury, lead, niobium, etc. Organic substances, uranium intermetallics. Ceramic compounds such as Chevreul compounds, copper-based oxides, and iron-based pnictides and chalcogenides. Semiconductor, semi-metal, and insulators like diamond and graphite. Early superconductor studies revealed that the superconducting state is influenced by the external magnetic field, the superconductor's internal current, as well as temperature. As a result, superconductors can be categorized based on a number of physical property-based criteria. Type 1 superconductors, materials that abruptly transition from a superconducting to a normal state and have only one critical field. Type 2 superconductors are those that have two critical fields, Hc1 and Hc2, and fall into a mixed state when they are between the critical fields. Under the lower critical field, Hc1, they are a perfect superconductor, and above the upper critical field, Hc2, they completely exit the superconducting state and enter a normal conducting state. Although thousands of superconductors have been identified, only type 2 superconductors, such as niobium-carrying alloys, copper-based oxides, magnesium diboride, and iron-based superconductors, are currently of practical value. Low-temperature metallic superconductors have now reached full commercialization and are used extensively in the electric power sector. Niobium-titanium superconducting wires were fully industrialized in 1968, just a few years after their discovery, and are now widely employed in practical applications. Since the raw ingredients and manufacturing costs of niobium-titanium alloy are significantly lower than those of other superconducting materials, it should be emphasized that it is still the least expensive viable superconducting material for applications in the liquid helium temperature range. Niobium-titanium superconducting wires are primarily employed in the creation of magnetic levitation trains, superconducting magnets, and MRI systems. Superconducting magnets that produce strong magnetic fields up to 9 Tesla at 4.2 K or 11 Tesla at 1.8 K are often made using niobium-titanium superconductors. Magnesium diboride has the greatest transition temperature among both binary intermetallic compounds to date. It is thought that this substance will eventually take the place of conventional low-temperature superconductors employed in liquid helium for applications at temperatures of around 20 K, which can be easily attained by liquid hydrogen or cryocoolers. Magnesium diboride is extremely appealing for extensive practical applications due to its plentiful raw materials and light weight. The Cuprate superconductors, which were found in 1986, currently hold the record for the highest superconducting transition temperature under ambient pressure. These materials' high superconducting transition temperatures and critical magnetic fields have proved essential for technological applications. Additionally, their fascinating superconducting and normal state characteristics have consistently pushed the boundaries of our understanding of solids. Cuprates are layered materials made of superconducting copper oxide planes that are separated by layers of ions like lanthanum, barium, and strontium that serve as a charge reservoir and dope the copper oxide planes with electrons or holes. This results in a structure that is frequently closely akin to the perovskite structure, which is defined as a superlattice of superconducting copper oxide layers separated by spacer layers. With only weak coupling between adjacent copper oxide planes and superconductivity occurring within the copper oxide sheets, the material's characteristics are very similar to those of a two-dimensional substance. A substantial anisotropy in the normal conducting and superconducting characteristics is caused by electrical currents flowing within the copper oxide sheets, with a conductivity parallel to the copper oxide plane being much higher than in the perpendicular direction. The chemical compositions, cation substitutions, and oxygen content all affect the critical superconducting temperatures. It is possible to produce these materials into useful forms such single crystals, wire, thick films, thin films, and bulks. Unfortunately, the use of these superconductors is constrained by flux creep, which causes the properties of high-temperature superconductors to degrade. The introduction of artificial pinning defects by chemical doping can help to overcome this problem. In bulk YBCO, for example, small amounts of chemical impurities within the copper oxide planes have proven to be very effective pinning centers that also do not significantly decrease TC. Because these impurities destroy superconductivity at nanometer length scales, which closely matches the superconducting coherence length, they are well suited for pinning magnetic flux lines in YBCO. Unfortunately, the normal region created by these impurities is restricted to the thickness of the copper oxide planes, and these defects behave as randomly distributed, point-like pinning centers that are ineffective for significantly reducing flux creep. One promising method to overcome this obstacle is to incorporate arrays of cylindrical inclusions with diameters comparable to the coherence length into superconducting matrix. Such extended nanodefects suppress vortex flux creep more efficiently than randomly distributed point-like defects. The Iron Age of high-DC superconductivity began in 2008 with the discovery of iron-based superconductors. Iron-based superconductors feature layered crystal structures and short coherence lengths, similar to cuprate superconductors, and exhibit strong upper critical fields and electromagnetic anisotropy. Despite having a lower superconducting temperature than cuprate, iron-based materials have a far lower anisotropy. For high-field applications that can operate at liquid helium temperature, as well as in a moderate temperature range of about 20 K, iron-based superconductors are particularly desirable due to their large upper critical fields and low anisotropy. According to certain ideas, a recently developed framework unifies the two families of high-temperature superconductors, cuprates and iron-based materials. To establish strong extended S-wave pairing symmetries in a square lattice, the unification argues that the latter is merely the counterpart of the former. The unification shows that the essential components of high-temperature superconductors are isolated d orbitals of cations that take part in strong in-plane couplings to p orbitals of anions near Fermi energy in a quasi-two-dimensional electronic environment. This would allow the anion superexchange magnetic interactions to contribute to superconductivity to the fullest extent possible. Special combinations between local electrical structures and crystal lattice structures are necessary to create superconductivity. The rarity of high TC superconductors is due to their specialty. It is explicitly predicted that materials based on transition metals will exhibit high TC superconductivity when they have a quasi-two-dimensional hexagonal lattice structure. Recently, a carbonaceous sulfur hydride with a critical temperature up to 287.7 K under extraordinarily high pressure of 267 gigapascal was reported to exhibit room temperature superconductivity. There is some debate over whether this result actually relates to superconductivity or whether it was misinterpreted for superconductivity. It appears that, for the time being, practical applications are still somewhat distant. The challenges to general adoption are the same whether superconductivity is attained at tremendous pressures, but at ordinary temperatures, it is not noticeably easier to do so. Furthermore, superconducting materials only last as long as extremely high pressures are maintained. As soon as pressures drop, so does the temperature at which superconductivity takes place. Making a room temperature superconductor without these high pressures is the next significant step, which has still to be done. Even while various technology, such as computers, maglev transportation, medical imaging, and much more, will improve, possibly the biggest gains will come from the enormous amounts of energy that may be saved in the electrical grid. The first family of unusual high TC superconductors was identified about 3 decades ago. Even now, many of studies have been published on these materials, yet it is still very difficult to comprehend how they become superconducting. Material complexity makes theoretical modeling challenging, abundant physical phenomena obscure our ability to identify primary causes from secondary causes, and inadequate theoretical procedures cast doubt on theoretical computation. Beyond all of these challenges and the lack of agreement, the main cause is the absence of successfully workable guiding principles from theoretical research to hunt for novel high-TC superconductors. We need to find new high-TC superconductors, but where and how? This question is still open.